Our paper is titled Learning to Selectively Update State Neurons in Recurrent Networks. I'm Tom, and this video is for CIKM 2020. So first off, a recurrent neural network is a powerful neural network designed specifically for sequential data, and it's been applied to a wide variety of problems that benefit from learning sequential dependencies in data, such as speech recognition, machine translation, sequence generation, and lots more applications. So the key idea of how an Rnn works is at every given time step or step of the input sequence, it's going to output a hidden vector representation of the incoming data. So we're basically going to maintain a memory state vector that gets updated over time as new information arrives. And the problem that we study in this work is that these states are typically recomputed from scratch at every single time step. And this is even true for the gating mechanism architectures, such as the long short-term memory or the gated recurrent unit. So our hypothesis is that we may not need to recompute the entire state. And because an Rnn's usefulness with respect to a task can be described by how the hidden state itself changes over time, a given time step, the state for a given time step may already contain a lot of information. So as you can see on the right, if we're updating from hidden state 1 to hidden state 2, some dimensions of the hidden state may change a lot and encode a lot of new information, and some dimensions may not change very much. And so the basic premise is, if we were to just, in this example, if we were to just not change the blue dimension, then the resulting hidden state would be barely different than if we did let it change. And so specifically the problem definition is, given the previous hidden state of an Rnn and the new input data, predict whether or not to actually update each decision of the hidden state in a binary way. So either update it or don't update it, and then actually apply this update. So why is this a hard problem? Well, first off, there's a sort of lack of supervision in that we don't actually know which dimensions should be updated, because they all interact in complicated ways. And by designing a complicated network like this, we're kind of assuming that we don't know how they should actually be updated anyways. Second, sort of ties into the first one, which is that these hidden state interactions, like the actual transitions that between the hidden states, are extremely complicated. And so by tampering with these high-dimensional and interconnected transformations, sometimes we can sort of see that the trajectories of the hidden state change in unexpected ways. And so we need to be able to handle that. And then third, the decision of either update or not update is by nature non-differentiable. And so we can't actually just train a model and use backpropagation directly. We have to do some sort of estimation along the way. And so in this work, we propose the selective activation Rnn, or the sa-Rnn. And the key contributions with respect to prior works on the same problem is that our method is now data reactive, which is to say, given two input sequences at a given time step, we might get two different predicted masks for which neurons to actually update. Most recent related works do something similar, but much of the older work up until a couple years ago is not data reactive. And then ours is also imposes no assumptions on the update patterns themselves. So some prior works will have different schedules for different neurons to update, and we just say, let's just learn it from scratch, and therefore we require fewer updates to the hidden state, as we show in the experiments. And the basic idea of how this method works is, at any given time step, we're going to predict which dimensions to update in the hidden state, and then we're going to actually compute only the new hidden dimensions for the hidden state. And along the way, we're going to try to minimize the number of updates to the hidden state. This is naturally a multi-objective optimization problem, where on one end, you allow the hidden state to update as much as it wants, and that'll achieve the maximum accuracy with respect to a given task of the Rnn. On the other hand, we don't let it update at all, and it doesn't learn anything about the input data. So somewhere in between, we're going to have high accuracy and very few updates to the hidden state. And we'll show that this exists in our experiments. So there are two key components of the method. Like, the first is the recurrence function, which is just an Rnn memory cell. In our experiments, we use the gated recurrent unit, or the GRU, as long as it predicts a hidden state at every time step. And then the second component is a small coordinator network that predicts the binary mask. And again, that is one value per element of the hidden state. And every value is either a 0 or a 1. And I highlight the word small because, in principle, we want to keep this component of the network very lightweight, so that we're not simply offloading the computation of the large neural network onto another large neural network, thereby taking much more time. The key component of the coordinator is that in order to make the decisions actually binary, either update or don't update, or 0 or 1, we have to use some sort of a binarization function. There's lots of different ways to do that. In this work, we use thresholding, which is by nature non-differentiable. And so as discussed further in the paper, we use gradient estimation techniques to actually make this work with backpropagation. And then ultimately at the end, we only update the proper dimensions to the hidden state. So how do we evaluate this approach? Well, the first set of tasks is time series classification, where we use 3 different data sets. The first is seizure detection from EEG data. The second is buzz event detection from Twitter data. And the third is an outlier detection task framed in a classification setting from Yahoo service metrics. The second is a language modeling task, which is we use the Penn tree bank, and it's basically to read natural language and predict what words will come next in a given sentence. So the Penn tree bank data set is a very standard language modeling data set. And then the third is the adding task, which is discussed in the paper. And the adding task is basically a synthetic and classic long-term dependency test for gated recurrent neural networks. And the major theme in our experiments is a good solution to this problem will have very few updates to the hidden state, and at the same time have good task performance, whatever the task performance may be. So as a quick warm-up, how do the update patterns between different compared methods actually differ visually? So we compare against 5 different baselines. The first is obviously random. The black dots mean we're updating at this time step. Time moves left to right. And a white square means we don't update. The first compared method is the Clockwork Rnn, which has different blocks of neurons that update at different schedules. So the first 5 neurons may update every time step. The second ones may update every other time step, and so on. The third is the phased Lstm, which you can see opens up one neuron for a certain amount of time, and then it closes it for a certain amount of time. And you learn the durations from the data. The third is the skip Rnn, which either updates the entire hidden state or updates none of the hidden state altogether, sort of in lockstep. The fifth one is the VC-GRU, the variable computation gated recurrent unit, which updates a certain proportion of the hidden state, and you just try to learn the proportion to update. And you can see that our proposed method on the right is very different from the other related methods in that some neurons never get turned on, some neurons get turned on for a long time, and then there's also a balance in between them. And it's learning these patterns directly from the data. So first off, time series classification, the way we measure performance on this is we use accuracy, and then we also measure how much of the hidden state was actually skipped. So we try to control all of the compared methods to make them skip roughly the same amount of neurons, and then we record their accuracy, and we take the geometric mean of the two. So sort of the measure we're looking at is the lower left of these tables, the geometric mean between the accuracy and skip percentage, which we want to be high. And we observe that in all 3 data sets, our approach is consistently the highest in this. And then also we record the floating point operations used in the entire network start to finish. And we see that our method is extremely competitive while having higher on average accuracy and skip percentage. Second, we look at the results from the Penn tree bank language modeling task, where we're measuring perplexity, which is an error metric, so the lower the better. And so that the utopian solution will be in the bottom left corner of this chart. And from these, again, we observe that our method on average is able to update fewer neurons while maintaining lower perplexity, so it's outperformed the other methods. And then an additional conclusion from this example is, or from this experiment, is that densely updating a small state is not nearly as good as sparsely updating a large state, which has implications for for the architectural choice in recurrent neural networks. And then finally, in conclusion, our approach, which is assumption-free update patterns, are cheaper to produce and are preferable across a variety of tasks. We showed very similar results on the adding task in the paper. Second, as I just mentioned, updating larger hidden states sparsely is better than updating smaller states densely, at least in our experiments. Third, it's true that hidden states already do contain a lot of information, which is in agreement with the gating mechanisms for LSTMs, or for RNNs, excuse me, along with residual nets and highway networks and many of their variants. And then finally, our method is very simple to implement and paves the way for new methods that can be more reactive to the input data with respect to the update patterns. So thank you very much. If you have any questions, please send me an email or ask me during the chat session. Thank you.